Alright, in this video we go over section 6.3 properties of trigonometric functions. In this section we're going to look at the domain and range of trigonometric functions, find the period of the specified trigonometric function, determine the signs of the trigonometric functions at given quadrants, and find values of trigonometric functions similar like we did in the previous section, but we are going to do it in a different approach, and then find them given a certain quadrant. We'll look at some of those examples and use even and odd properties to find values of trigonometric functions. Well, this box right here summarizes the domain and the range of all the trigonometric function sine. Well, sine and cosine have if you remember, they have, well, we haven't looked at the graph for those, never mind. The domain of and range for sine and cosine is all real numbers. They're not undefined at any value at all, and the range go from -1 and 1. And then the ones that are a little bit trickier in this case, well, are tangent and secant, whose domain the domain excludes all odd multiples of pi over 2. Okay, and cosecant and cotangent, they exclude all multiples or integer multiples of a pi. Well, we're gonna look at a little bit more about this later in this chapter when we look at the graphs and when we evaluate inverse trigonometric functions. Now, determine the period of a trigonometric function. Well, it turns out that sine and cosine are very special functions. They are functions that if you evaluate sine and cosine at an angle plus multiples up to pi, you are really evaluating the angle, the sine of the angle theta, with subtracting those multiples of pi and 2 pi. And that's because, again, if we recall from the unit circle, we go around the circle and we fall into the same values after one rotation. One rotation is 2 pi, another rotation is 2 pi. Let me just give you an example. For example, in this case, if we go back to our unit circle, well, so this is 0 or 2 pi. This is pi. If I go 3 pi, well, I need to go pi first and then another turn. That'll be 3 pi. And if I do 2 pi more, that'll be 5 pi, and then 7 pi, and then 9 pi. But in this case, I'm still falling within the same point. That doesn't, and the values of the trigonometric function do not change at all. So what about this? Well, it would be a good idea to look at some of the examples. But before that, well, let's define what a periodic function is. Well, in this case, a periodic function is a function of this form. A function that evaluated at theta plus some value, which is the period, which is the value in which the function repeats itself again, is the same as evaluating the function itself at the given angle. So in this case, well, these are the periodic properties of all trigonometric functions. So these are very one thing we need to be very, very careful. Sine and, like we mentioned in the previous page, sine and cosine share the same. Oh, wait a minute. Sine and cosine share the same period, right? Sine and cosine 2 pi, and of course, it wouldn't be no surprise that they are inverses respectively, like cosine of sine and secant of cosine. They share the same periodicity. And on the other hand, well, in this case, tangent has a different period, and later we will have a better picture of why the period of the tangent function is pi as opposed to the other four functions whose period is 2 pi. And we are going to use these properties in order to find the exact values of the following angles. For example, evaluating sine of 17 pi over 4. Well, if you look at 7 pi over 4, and in this case you can see the picture, so that's one turn, another turn, and then this little piece which is the 17 pi over 4. Well, looking at the picture, it clearly is a pi over 4. I'm going to show that this is pi over 4 or 45 degrees. But well, how can we do this? For example, in these examples, we have the graphs of this. But what if you were just given this expression, evaluate, simplify, well, without having an idea of how the angle looks like? Well, first I'm going to decompose this 17 pi over 4 in a way that I get a 2 pi over 4, a 2 pi plus some other angle. So how can we do this? Well, so this is, what am I going to do here? I'm going to split this into 8 pi and 9 pi over 4. Alright, well, where did I get this 8 and this 9? Well, 8 plus 9, that's a 17. But what I want in this case is that one of the ratios when splitting this, like in this case 8 pi over 4, gives me a 2 pi, so I can use the 2 pi, in this case sine of theta plus 2 pi, so that's going to be sine, well, I'm gonna put the 9 pi over 4, and 8 pi over 4, that's a 2 pi. Alright, if we compare forms, 2 pi and 2 pi, and then in this case 9 pi over 4 is the angle theta, so ultimately, in a way, this 2 pi simply goes away, and it goes like sine of 9 pi over 4. Alright, and then I'm going to do the same. I'm going to do the same for let me put this below because I may not have enough space. I'm going to do the same again in a way that one of the terms when simplifying gives me a 2 pi, like in this case pi again plus 8 pi. Well, pi over 4 plus 8 pi over 4, that's 2 pi. Alright, and again, comparing forms, 2 pi theta. 2 pi theta. So in this case, sine of pi over 4. The 2 pi disappears, and again, like I mentioned, well, we have the picture, and again, we can clearly see that this is a 45-degree angle, right? But we needed to show by decomposing this number using a couple of steps so we can get this far. Alright, sine of pi over 4, we can just use our unit circle. Well, we got to pi over 4 or 45 degrees. Either sine or cosine, they are the same at that point. Square root of 2 over 2. Final answer. Okay. Let's do another example. Well, cosine of 5 pi is going to be, I guess, a little bit easier to do. Well, cosine, I'm going to break it up into 3 pi plus 2 pi because 2 pi plus 3 pi equals 5 pi. But this 2 pi right here, I will use it to make it disappear by using the, in this case, the periodic property of cosine, which in this case is, well, simply cosine of 3 pi. Alright, I guess 3 pi it's still bigger than 2 pi. Well, we need to break it up further as cosine of pi plus 2 pi. And again, by periodicity, by a periodic property, well, this is theta, which is pi to pi, and that just goes away. Cosine of pi. Alright, So ultimately 5, what we're doing here is showing that 5 pi, it's the same as pi. Now, well, what is cosine of pi? Well, we're going to go to pi or 180 degrees. Cosine, again, keep in mind that's the x-coordinate, while sine is the y-coordinate. So cosine of cosine of pi will be -1. All right, let's do an example with tangent, but be careful for the tangent one because the period for the tangent function is not 2 pi as opposed to the other function. In this case, tangent, and its co-function, which is called cotangent, have a period of pi. So somehow I have to make this look like a tangent of let's see. Simply pi plus 4 pi over 4. On the one hand, well, pi plus 4 pi is equal to 5 pi. And then when I simplify this, that's going to give me 4 pi over 4, the pi that we want, to simply make it disappear and simplify the expression. Well, on the one hand, I'm going to have tangent of pi over 4 plus 4 pi over 4, that's simply pi. Comparing forms, okay, this pi is going to go away and this pi over 4 is going to remain. Alright, so in this case, what are we going to have? Tangent of pi over 4, which in this case, well, let's go to our unit circle. Well, pi over 4 or 45 degrees. Well, in this case, tangent is defined as sine over cosine, that is y over x. And in this case, if we divide root of 2 over 2 by itself, that's simply going to give us, so I'm going to write it down, the square root of 2 over 2 divided by itself, that's simply 1. All right. And that is how we can simplify. We're looking trigonometric expressions with angles that are actually way bigger than 2 pi. And we do that by breaking this up into two terms in a way that, well, for the sine and cosine function, we need a 2 pi. But for the tangent function, we need a pi instead. All right. Let me actually circle this just so you can see how these are gone. All right, this one goes away as well. All right, let's look at the next page. Well, determine the signs of the trigonometric functions in a given quadrant. Well, so what are we going to do in this topic? Well, so first quadrant, in the first quadrant, we have that all trigonometric functions are positive. Second quadrant, only sine and its co-function, cosecant, is positive. The remaining functions are negative. Third quadrant, only tangent and cotangent are positive. The remaining functions are negative. And on the fourth quadrant, only cosine and its co-functions secant, and I mean its inverse secant, not its co-function, its inverse rather, are positive. The remaining four functions are negative. All right, in a more visual way, well, we have that, okay, quadrant 1 all positive. Sine and its inverse, it's only positive. Third quadrant, tangent and its inverse, and cosine and secant on the fourth quadrant are positive. Well, you might have heard this mnemonic before. Well, that tells us that A, S, T, C. All students take calculus, and this means this is just to remember that A stands for all. Let me actually highlight this. Stands for all. All right. S stands for sine, and of course its inverse cosecant. The T stands for tangent. and the C stands for cosine, in which they are positive. And of course, they are in its mini. You can see them in separate in its own, in its standalone Cartesian plane. So let's have a look and determine, for example, in this next example, name the quadrant in which the angle theta lies if sine is positive. Well, this greater than 0 means positive, and cosine less than 0 means negative. So let's put some sign that means positive and negative. So we're going to look for a quadrant in which sine is positive. Well, in the first quadrant, sine is positive, but keep in mind that all are positive. We're looking for a quadrant in which cosine is negative, and in this case, that quadrant is the second quadrant. All right. Now let's look for the quadrant in which tangent is positive and cosine is negative. Well, let's see. That quadrant will be the third quadrant, because in this case, if you look at this, tangent is positive. Here, tangent is positive as well, but we need cosine to be negative. In this case, that's where it's negative, the third quadrant. And last but not least, name a quadrant in which secant is positive and sine is negative. Another way to say this, that cosine is also positive, right? Because this is the inverse of each other, in this case positive and then negative. So we want cosine to be positive, sine negative. Well, cosine is positive in the first quadrant, and so the remaining 5 trigonometric functions are. But we want a quadrant in which the sine function is negative, and that is the fourth quadrant. All right, fourth quadrant. All right, so let's move on to the next page. Let's see what we have. So, okay, finding values of trigonometric functions using fundamental identities. Well, so in this case, okay, just give me 1 second here. I feel like I lost some of the charts. All right. So, finding values using fundamental trigonometric identities. Well, we sort of look at these identities in the previous couple of sections, except the Pythagorean identities. So later in the future, I mean, you will, after using them all up, applying them in the exercises, you will be able to simply come up with its values, or come up with in a very intuitive form. So keep in mind that cosecant is the reciprocal of sine, secant is the reciprocal of cosine, cotangent is the reciprocal of tangent. I had it twice just so you can see, or another way to say this is 1 over tangent. All right, and then sine squared plus cosine squared equals 1, and then this remaining 2. All right, let's do an example, and we already sort of did this in the previous section, but now we focus on using the trigonometric identity. So, given sine square root of 5 over 5 and cosine 2 root of 5 over 5, find the exact values of the 4 remaining trigonometric functions using the identities that we have on the top of the page. Okay, I'm going to leave it here. Well, we have sine and cosine, we need tangent. Tangent theta, which by definition, tangent is sine divided by cosine. And those sine and cosine, we are given those functions, right? So in this case, sine, which is square root of 5 over 5, and cosine, which is 2 square root of 5 over 5. So when we simplify this, well, we can just cancel square root of 5 with square root of 5, and 5 with 5. We are going to be left with 1/2 as a final answer. All right. Let's look at tangent. I mean, not tangent, but actually cotangent. All right. Let's look at the cotangent function. So, cotangent is the reciprocal of tangent, which is cosine over sine, or 2 over 1. We can simply say that's 2 over 1 because that's the reciprocal of tangent, or which is the same as simply 2. Secant theta, which is defined as 1 over cosine, the reciprocal of cosine. Well, what's cosine for all in this case is this value of 2 root of 5 over 5. So 2 root of 5 over 5, that whole under 1. All right. Well, in this case, dividing by a fraction is the same as multiplying by the reciprocal. So this is going to be 5 over 2 root of 5. But as a final answer, MyMathLab may ask you to rationalize denominators, and all we have to do in this case is multiply and divide, or multiply numerator and denominator by the radical factor. All right, so in the numerator, I'm going to have 5 times root of 5, which is 5 root of 5. And in the denominator, I'm going to have 2 times root of 5 times itself, which is reduces to 5. Okay, keep in mind that root of 5 times itself is the same as when I multiply these two together. It's the same as doing this, which really cancels, and it gives me 5. And then in this case, we're good to just cancel these two out, leaving us with root of 5 over 2. All right. And last but not least, we need to find cosecant of theta, which is in this case the reciprocal of the sine function. And we are given that the sine function is it's root of 5 over 5. So 1 over root of 5 over 5. But again, we are dividing by a fraction, multiplied by the reciprocal, 5 over the root of 5. Okay, but again, you might want to rationalize the denominator. Okay, 5 root of 5 is simply 5 root of 5. 5 root of 5 times itself, it's 5 for the same reason as in the previous step or in the previous part of the example. And again, we're going to have this very same situation in which we can cancel these 5s. So final answer, square root of 5. Well, let's look at some other types of examples in which we are going to apply this aforementioned fundamental trigonometric or trigonometric identities. So in this case, rather than putting all this in the calculator, so we are going to pretend that we do not have a calculator with us. Well, we are going to simplify using identities as well. We cannot find tangent of 20 on the top of our heads, but we have this sine over cosine that we can transform, and then we are going to do some really nice simplification here. Well, keep in mind that sine over cosine equals to tangent, so I'm going to apply this to this example. So tangent of 20 degrees minus sine over cosine, which is also tangent. And in this case, well, same quantities, 0. Whatever this is minus itself equals to 0. Sine squared of pi over 12 plus secant squared of pi over 12. Well, in this case, the trick right here, also most of the times it's when you have like secants or stuff like that, is to convert to sines and cosines. Well, let me before just to justify what am I going to do, well, before I do, I would like to justify something. So in this case, it turns out that, well, like in this case, cosecant, or rather secant equals 1 over cosine. In this case, it is also true that so secant theta equals 1 over cosine theta. It is also true, this holds true for secant squared theta equals to 1 over cosine squared theta, or even more for secant to the 4th power, for example, or to the 7th power, to your favorite power. And that's because we can basically raise both sides of this identity to the nth power, and well, secant to the n, that's secant to the nth power theta equals 1 to the nth power. It's only 1, it's always 1 cosine to the nth power in the denominator. All right, so in other words, these identities right here, at least the first 1, 2, 3, 4, 5, they work if you raise them to any power, which is what I'm going to do here. In this case, 1 over secant squared is the same as turning this into the reciprocal, and its reciprocal, or its inverse, is cosine. So I'm going to do sine squared of pi over 12 plus, and in this case this is going to be cosine squared of pi over 12. And well, what do we know? This one might look a little bit complicated. However, sine squared plus cosine squared of whatever angle, you can have your favorite angle here as long as it is the same on both terms, which it is the case. It doesn't matter if you have a 5 and a 5, 50 million and a 50 million, or minus 7 and a minus 7. This is always 1. Final answer. All right. Let's move on to the next topic. Again, we're going to move on to obtaining values of trigonometric functions in different ways. Well, using a quadrant or using identity. So, and the way we are going to have this this exercise presented is going to be a little bit different. We're not just going to be given, like in the previous example, sine, explicitly sine and cosine to just find the remaining function. So in this case, they're going to give us only one trigonometric function and the sine of another function. And this is going to be enough information to find the remaining 5 trigonometric functions. All right, there's going to be 2 options. Option 1, using a circle of radius r. Okay, in this case, we're going to draw a circle and use the trigonometric function and its value, using its value depending on x, y, and r. And then we may need to find that. Sometimes we may need to find the radius of the circle. Sometimes we may need to find one of the angle. I mean one of the lengths of the sides, either the x or the y, because we will be given r the radius. All right. And so let's go ahead and do the example that we saw, just so you can see what we're up to. All right. So for example, okay, option 1, using a circle of radius r. So let me do a circle here, and in this case, well, tangent is equals to 1/2. If you look at this, tangent is positive and sine is negative. So we need to go back to our to a couple pages back. So we need to find the quadrant in which tangent is positive, yet sine is negative. And in this case, it turns out that this is the third quadrant. All right. Well, this one might look a little bit trickier. Let me walk you through this one so you can see the real trick to this. Okay. So in this case, I mean, because if I say, well, tangent by definition equals y over x. In this case, it would have been the point 1 comma, actually 2 comma 1, because in this case x equals to 2, y comma, which would be somewhere here. All right. However, in this case, we want sine to be negative, so it cannot be in this point, in this quadrant. It has to be over here in this quadrant. So in this case, it has to be the other way around. We need to write this tangent theta equals 1/2 as negative 1 over negative 2. Negative over negative, it's still positive, but in this case we make sure that cosine, oops, over here, that sine is negative, cosine is also, well, we don't care about cosine, but we will actually. So in this case, let me put the point over here to negative 2 comma negative 1. Okay, so let's see. Sine theta, that's if we go back a couple of that's y over r. So but in this case we need to find the value of r. All right. Or in this case, actually, we can skip that part. We can skip the y over r, because we know explicitly this is cosine, this is sine, and in this case, simply negative 1. Cosine theta equals to the x coordinate, which in this case is negative 2. Tangent, well, I'm going to write it again, but in this case, it's given. That's 1/2. Cotangent, it's cotangent in this case is by definition, well, instead of I'm not going to use trigonometric identities in this case. In this case, I'm going to use the circle of radius r. I'm going to find that radius r, okay, using the formula that we have here. All right, so square root of x squared plus y squared, and in this case, well, the square root of x, which is negative 2, plus negative 1 squared. But of course, those negatives are going to go away, because a negative quantity squared becomes positive. So that's going to be 2 squared, which is 4, plus 1 squared, which is 1, which is the square root of 5. All right. So in this case, our radius is square root of 5. So by definition, well, in this case, if we go back to the definitions from a couple of sections ago, in this case, cotangent is x over y. All right. In this case, so this is x, this is y, negative 2 over negative 1, simply 2. Of course, if you look back to tangent equals 1/2, it's reciprocal. That's using identities. In this case, again, I'm using the circle of radius r. And then we need secant and cosecant, which by definition, let me go back to that page. It's page 2 on section, I believe, 6.2, if I'm not mistaken. Secant is 1 over x, cosecant 1 over y. One over x, 1 over negative 2, which is negative 1/2. and 1 over y, which is 1 over negative 1, negative 1 over 1, which is negative 1. And that's how we get the remaining of trigonometric functions. Personally, I prefer using identities rather than a circle of radius r, because I mean sometimes it might be a little bit tricky when it comes. So like, what if we were given sine and one value? Well, in that case they're really giving us r and y, and y, and it would be a little bit trickier to find the value of r. So my advice is to do it the other way around, using option 2, which is using identities. All right, so let's see how are we going to move on through this. Okay, so option 2, using identities. Well, we know that tangent theta equals to 1/2, right? But by definition, tangent is the same as sine over cosine. So we can simply relate these two and relate this one, these other two. So we have tangent, that's given. Well, sine sine theta equals to 1, cosine theta equals to 2. Well, tangent is given, cotangent theta, which is simply it's simply the reciprocal of the tangent function. Okay, let me bring that up again. Cotangent is the opposite, or I'm not the opposite, the reciprocal of cotangent. So all we do is the reciprocal of 1/2 equals to 2. And then secant, cosecant. This is not cosec, it's cosecant, CSC theta. Secant is the reciprocal of cosine. Well, this is 1/2. And in this case, cosecant is the reciprocal of sine. However, we're a little bit in trouble here, because if you notice, I didn't get the exact same signs as in the previous form of doing this, right? And that's because I'm getting everything positive here. So in this case, I need to make sure that sine is negative and also cosine is negative. Cotangent is also positive, secant, and cosecant is negative. How do we get all that? Well, again, keep in mind that they're telling us tangent is positive and sine is negative. So what is that quadrant? Third quadrant. And if we go to the third quadrant, okay, let me go back another page. Third quadrant, only tangent and cotangent are positive. Everything else, sine and its reciprocal, which is cosecant, and cosine, which in its reciprocal, which is secant, they are all negative. So that's why we just need to change the signs of this. Okay, again, tangent's positive, cotangent's positive, the remaining are negative. All right, one more exercise, and we are essentially done with this section. Well, using even and odd properties to find the exact values of the trigonometric function. So if you recall from chapter, I believe it was chapter 2, when we covered in even and odd functions. Well, a function is even if f evaluated at a negative value, we get the same as evaluating the same function at the positive input. And otherwise, it's going to be odd if we evaluate the function at a negative value and its output is negative, the function. Well, in this case, the only functions that turn out being even in this case, in other words, that you plug in a negative, the negative disappears, are the cosine and its reciprocal, which is secant. On the other hand, well, the functions that are odd, in other words, that if you evaluate a negative angle, the negative goes outside of the function, in other words, changes the sign. These are odd, are the remaining four functions. All right, again, keep in mind that if we were looking at the graphs of this, well, cosine and secant, as opposed to the remaining four, are symmetric about the y-axis. The yellow, the ones that I highlighted in yellow that are odd, are symmetric about the origin. All right. So we're going to use these values to, in a way, try to get rid of this negative angle. So, for example, because sometimes it's a little bit weird to go in the negative direction of the angle, because the most common convention is to go counterclockwise rotations. But when it comes to negative, well, it could be a little bit tricky. So what we're going to do in this case, well, it's use what is this? Use this even odd properties to, in a way, either get rid of the negative sign or simply or take it outside. Well, sine of negative 45 degrees. Well, what do we know about sine and its evaluation and negative values? Well, we can, in this case, put the negative sign in front of the sine function, and that's 45 degrees. All right. So all we have to do is evaluate sine of 45 degrees. Well, we already did that. That's square root of 2 over 2, but with a negative sign. Now, if you didn't use the even odd property, well, you go in the other direction, in the negative direction, to negative 45 degrees, which is 7 pi over 4. What sign? Isn't it negative root of 2 over 2? It is, right? Okay, what about cosine pi? Well, the cosine function, when you have a negative angle, the negative simply disappears. That's cosine of simply pi. And what do we know about cosine pi from the unit circle? Negative 1. Now, tangent of 37 pi over 4. Oh boy, this one is going to be a little bit of a mess, because it's going to be a really huge angle. So what we're going to do, this is I'm going to take out the negative sign, because the tangent function is it's an odd function, so that's going to be negative tangent 37 pi over 4. All right. And in this case, we need to figure out what 37 pi over 4 is in this case. All right, if we do the subtraction by pi all the time, well, that's going to take forever to do 37 and 36 and blah, blah, blah. Well, in this case, if we go back, let's go back to the first page of this handout. Okay, and add an extra piece of information. Well, sine and cosine are periodic at integer multiples of 2 pi, like 4 pi, 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, 12 pi, etc. And of course, negative values. However, the tangent function is periodic at n multiples of pi, whatever n is, whether this is odd or even, doesn't matter. This is the same as tangent of theta, and that's how we're going to simplify this guy. Well, so that's going to be, well, 37, that's going to be 36. I'm going to do 36 maybe not 36, or yes, 36 pi over 4 plus pi, because 36 plus 36 pi plus pi, that's going to give me back the 37. And well, 36 over 4, pi over 4, negative tangent of, I'm going to do the pi over 4 first. And then 36 over 4, that's a 9 pi. Alright, and again, this can be treated as n pi. In this case, n is 9. This is simply negative tangent of pi over 4. And what is tangent of pi over 4 using the unit circle? Pi over 4 is, the values are root of 2 over 2, comma root of 2 over 2. So in this case, tangent is sine over cosine, or y over x. And well, notice we have the same number. That's simply 1, but it carries the negative sign. Alright, so this is the end of this video. It's a good place to quit. I'll see you in the next one.